So, hi everyone to today's last talk about what the GC team has been doing since JDK 9. My name is Thomas Schatzel. I'm from the Abortable Java Hotspot virtual machine GC team. So I'm standing here chained to the desk, and two somewhat awkward thoughts cross my mind. First, this one. And second, we've been hearing a lot of great talks today about the future of Java, what has been done in Java, how to use Java, how to improve it, and now you get a talk that's about the guts within the VM. And while I try to tone it down a bit, it's going to be a bit technical. Well, bad luck. Anyway, I've brought with me 5 improvements we've been working on since JDK 9 and a call for participation, because we think that the GVM lives and dies by your input, and I'm going to tell you what you can do. But let's start. So first, parallel full GC. So there's always been the problem that the G1 full GC is very slow. I mean, it's serial, things-threaded. So G1 has very high worst-case latencies and really bad throughput. So in this change, we tried to make the G1 parallel full GC on par with the parallel GC full GC. And the solution was basically, make it parallel. And here's one slide about some results with that. So basically, we are comparing G1 parallel full GC with parallel GC full GC on a few applications that I found rummaging in the bug tracker, on the mailing lists, and they should kind of represent applications with different liveness, different connectivity. And there's the system GC test that performs many system GCs on a very small live set. This big RAM tester application, or micro benchmark basically, that's basically a big LRU cache. It means a big array, and you add array of references, and you add and remove objects in an LRU fashion. That has, at the point of full GC, a huge live set and lots of references, and there's this tree fragger or fragger. That's a fragmentation-inducing benchmark from Red Hat with a medium live set. And without going into the detail, it looks we are there.
Do you know how many cores this tracks?
I think 32 or something like this. Yeah. Okay, for everything fine. This is available since JDK 10 build 33. Then let's go to the next topic. Sorry, has there been a question? Okay. Faster card scanning. Now you will likely ask yourself, what's card scanning? What's card scanning? So let me explain that a bit. In this figure, you can see the Java heap that is split in regions, the blue boxes. It contains objects, there's references between each other. And during GC, we are going to move that one object. Now we have a problem, what we are going to do with these references. I mean, if we just continue the application, it would very likely crash at some point when dereferencing them. So there is something called remembered set that, as the name implies, remembers the locations where there are references from other regions to a particular region. But what does it and that using that, we can fix up these references and the application is ready to go. But what does that have to do with cards and scanning? Well, the elements of the remembered set are not the actual references to the references to the Java objects, but to so-called cards. That means small subdivisions of the memory. And to actually find the references, you need to scan that area. And you need to scan this area quickly. So the solution for this change was to refactor and improve the current existing scanning code. That means the code has been really, really overly generic. It has been replaced by specialized code for different situations. This allows us to manually subsume and remove lots of checks in the code. And just showing you results, this is these are the pause times of this big RAM test application, which incidentally also has spends tons of time on this card scanning phase before that change, and yeah, that's the pause times afterwards. Nice thing about this, also available in JDK 10. Now let's get to what we have been working on lately, and that's not in JDK 10. First one is what we call rebuilding the remembered sets concurrently. So there's a problem with G1, and that's the remembered set. They take a lot of memory. We've known instances where 20% of the total heap size is taken just by the remembered set. Like if you have a 100 gig heap, the remembered set takes 20 gigs, which is bad. The upper bounds are actually even higher because this is an O square of the regions relation. And yeah, what has been noticed is the old regions use the most remembered set memory, and I'm going to try to show you why by showing you how the remembered set and the objects within a region change within the GC cycle that is shown above that heap snippet. So at the beginning of the collection cycle, there are a few young-only, so-called young-only GCs, and during that time, new remembered set entries are added to the remembered set of the region, and at some point, G1 decides to start marking. The heap got full enough, and so it starts looking at which region it can evacuate. Okay, now liveness analyzes that its marking is working. During the time, the application continues working, more young-only GCs happening. And at some point, there's this so-called remark pause. At the time, the liveness of the objects within the region has been determined. But at that moment, actually, G1 could immediately start evacuating that region, that moving the remaining live contacts somewhere else. The problem is the remembered set. It's pretty big, as you might have noticed at this point. And so it tries to kind of remove obsolete entries. That means entries that cards that do not contain any live objects. For this to happen, it needs to do another concurrent phase that's called create live data map since JDK 9, where it creates that map that is then uses to scrub the remembered sets from those obsolete entries. And during that time, the application continues working, adds remembered set entries to the remembered set, of course. And at some point, there's this so-called cleanup pause where first we know the liveness of the objects in that region, and we hopefully got rid of a lot of remembered set entries. That means cards to scan during the GC to evacuate that region. Unfortunately, for some reasons, we can't do the so-called mixed GC immediately. We need to wait for another young-only GC, but then finally we can do that. There are two cases now. One is that the region gets evacuated, and that's a nice one. The remembered set gets completely dropped on the floor, and that region is empty, can be reused. But what happens if that region is not cleaned up, and the G1 decides to not evacuate that region, and that from multiple of those garbage collection cycles? Well, the remembered set gets bigger and bigger, while it always removes actual entries from it. There's some fragmentation in the memory there, and that's why it gets really big. Some key observations. G1 maintains the remembered sets all the time for all regions. I mean, if you think about it, and after seeing this animation, you will notice that G1 actually needs this remembered set, at least for old regions, only during these mixed GCs. All the other time it doesn't need it. And the other issue is that removing those obsolete remembered set entries is costly. I mean, you need to create this live data map. During the cleanup pause, you need to scrub what we call the remembered set, which can take a few hundred milliseconds actually, which you don't want. So the solution here is only keep the required remembered sets when really needed. That means only for regions that are in the so-called collection set. That means regions that we are probably going to collect in the future, which is much less than all regions. And of course, that minimizes the fragmentation in the remembered set. For that to work, we have to construct these remembered set concurrently between remark and cleanup, which is bad, but at least we don't need to do anything in the cleanup pause, which is bad for latency. So there is some prototype, some internal prototype, which and there are some side effects. It lengthens the time from remark to cleanup. What we measured was up to 30% longer concurrent marking cycles, which we think isn't that much of an issue, particularly because the dynamic air hop feature that determines when to start the marking, that means schedules that initial mark pause, will automatically adapt anyway. Other nice side effects are it improves throughput and pause times. Throughput because outside of the rebuild remembered set phase, you don't need to update the remembered set at all. All that work goes away. And you create, and from a pause time point of view, since you create the remembered sets only at the time when you need it, there is little fragmentation in it. Actually, you probably noticed that I didn't say anything about trying to scrub these remembered sets anyway. So, and the feature for the container guys, it allows G1 to implement a bounded remembered set in terms of memory usage. That means when rebuilding, G1 could just stop collecting remembered sets for particular regions if some budget has been exhausted, which has always been a problem. I mean, 20% of the heap is probably too much if you make that kind of safety buffer. So some numbers on that. Memory usage on that big RAM tester application. In the baseline, the remembered set takes 10% of maximum heap size, which isn't too bad. But in the prototype, outside of the rebuilding and the mixture C phase, the remembered set only takes 0.5% of the total heap anymore. At the end of rebuilding, though, you still need 7.5% of the total heap size. When rebuilding the remembered set for around 60% of the heap. This is due to various reasons. There are some constant costs. And G1, if the remembered set doesn't contain too many entries, it uses a less dense representation of the remembered set. And this selection policy for the regions to rebuild the remembered set for is pretty simple at the moment. So how does this look like from a pause time point of view? This is the same graph as before from the faster card scanning change. And this is what it looks like now after that change. More information can be found on this backtrack entry. It's a work in progress. It may or may not land in JDK 11. Now, for the next change, we're currently working on abortable mix collections. So G1 strives to keep some kind of pause time. And it does that by determining the collection set. That means the number of regions it's going to collect at the start of the garbage collection, and then just does everything in one go without caring about the current time while doing so. The problem is, particularly during mixed collections, predictions are pretty hard to do. And G1, unfortunately, mispredicts pretty often. I mean, you can tune the mixed collections to keep the pause times, but it's pretty hard. Let me show you how this looks like. So you have this heap with some young regions, some old regions, and some free regions. And there is this collection set, if you want, which contains these young regions and these 4 old regions at the bottom. And currently, during garbage collection, G1 just takes all those regions, copies the contents over either into new young regions or old regions, and yeah, maybe it can happen that the pause time is exceeded, bad luck. So this solution that we follow here is to incrementally collect the collection set and abort the evacuation if the next increment would take too long. It's easier to predict the evacuation time for smaller parts of the heap than for larger. So how would that look like? The same collection set, and G1 starts by collecting the young regions. That takes some part of the pause time budget. Now G1 sees that there is quite a bit of budget left, so it takes 2 old gen regions. Well, still quite a bit of pause time left, but not as much as before. So it just evacuates 1 old regions. Now we are getting really close to pause time goal, and G1 simply says, yeah, stop the garbage collection. We are probably going to exceed the pause time now. Yeah. So there is some performance impact of that abortable mode. So the idea is to only enter this abortable mode if needed to decrease that overhead. More information can be found at the bug tracker entries. Again, work in progress. It may or may not land in JDK 11. And on for the last of the changes I want to discuss today, and that's automatic thread sizing. So one problem of G1 and basically all of the collectors is that manually setting the number of threads correctly is impossible, and in many cases not even desired. I mean, if you want to run your installer, your tiny installer on a machine with 2,000 threads, you don't want that installer to launch, 1,500 threads. That doesn't make really sense. Anyway, if you wanted to try to set this right number, it's a lot of work because it depends on the hardware, on the application, and actually it depends on the current application phase you are in. And to make matters even worse, in the hotspot JVM, you can only set the number of threads statically at the start of your application of the VM. So basically, you can't do that. But there are certain benefits on using the right number of threads for the correct situation, because it saves resources, threads, memory. It has some faster startup, and actually it improves pause time. And our solution that we are going to implement here is to let G1 automatically decide this number of threads, because I mean, G1 already takes a lot of statistics about GCs, how long it takes to copy a certain amount of objects, how interconnected they are, and such things. So it seems obvious to let the garbage collector decide that. And actually, G1 is cheating a bit, since JDK 9, some phases of the garbage collection actually do exactly that for performance reasons. I brought some graph of some random application here, which at the beginning has some longer pauses because it starts up, moves stuff, initializing in some kind of database, if you want to say so. But after that, there's not much activity going on. If you look at the right side of the graph, it shows the number of threads used during the evacuation phase. The light blue line, which basically shows the current state of the VM, we always use 28 threads, whatever the situation is. But in our prototype, Basically, at the start, when there's lots of activity, G1 will ramp up the number of threads to use really aggressively, but then drops them down to 3 in that case. And looking back at the left graph again, which shows pause times, well, actually, it improves pause times a little, which is nice, but yeah, we'll take it. More information can be found in this JAP, draft JAP, or in that backtrack guide. Again, that's work in progress and will land in some release in the future. So let's get to the last topic I have here, participate. We would like to have you participate because well, it helps us a lot to improve G1 and also the other collectors because we want to know what is the right thing to improve. I mean, I mentioned and used this big-RAM test application. That's an application that has been attached by some user after noticing that his application doesn't work at all. And yeah, we will look at this stuff and fix it. We know that not everybody can contribute on the same level, but there is a lot of things you can do. Probably the easiest thing and the least time consuming is hanging out on the hotspot GCUs main list. Report your failures, report your successes, which is also pretty nice, and provide answers to the community. If you think you want to start with development, fixing small bugs, in the bug tracker, at least in the GC team, we label all our bugs that are simple with some labels called start or clean up. Browse through it, look through it, and yeah, come to Hotspot GC Dev and discuss them. Even if you don't have a fix, we're happy to help. But I also brought some interesting larger projects for the pros of you to do, and which would be nice for G1, of course. And they are called method barriers, throughput barriers, and NUMA support for G1. Just a few quick notes about each of them. method barriers. So there's a functionality in the compiler that's called method barriers, and that's basically some small piece of code that is run before a method, and a method is entered. And that could be used to improve the throughput of the G1 collector. In particular, G1 uses so-called write barriers for every reference write. And that write barrier, or part of that write barrier, isn't used all the time. Actually, it's used only during the very, very small marking part of the garbage collection cycle you saw before. And although, but at the moment it's in all the time, it's active all the time, there needs to be some code executed for that, and that, as I've learned yesterday, could give up to 3% of throughput. So what some method barrier could do is, during the time when it's needed, remove that so-called pre-barrier and exchange it by NOPs. That means no operations, and basically every CPU can do nothing pretty fast. Throughput barriers. So G1 has throughput deficiencies. Everybody knows them. Mostly write barrier related, and this time so-called post-write barrier related. And there's a possibility actually to be as fast during application time, or almost as fast as parallel GC. And that would be by actually using the same barrier as parallel GC in G1 at the cost of some little extra work during the pause, which may or may not actually have an impact. More information about this, my colleague Eric Duveblad had a really, really good talk about this last FOSDEM. And now let's get to the last item I have brought with me, and that's NUMA support. Yeah, it would be really, really great if we could improve throughput on large multi-socket machines by exploiting memory locality into one. There is a lot of opportunity to get really, really good numbers. There's the JAB that is actually open for 6 years now. Maybe somebody wants to have a try. And that's it for me already. Questions?